This video looks at what is meant by the terms coordinate and non-coordinate bases, and how each is derived in relation to vectors and one-forms. An example is then given using spherical polar coordinates and the basis that can be formed in this coordinate system. So a natural choice for basis vectors involves the use of the derivatives of the coordinates xi to define basis vectors. And the symbol for basis vectors is this one, the familiar one, or this one. We've seen this one in the previous video on directional derivatives, or more compactly written in this form, d subscript I. And basis one forms, e contravariant I here, is dx contravariant I there, or nabla del xi. So any vector v can be written as v equals v contravariant I times the basis vectors e subscript or covariant I. Same here, another form here, using this object here, this derivative operator we've seen in the directional derivatives videos. Or in this form here, where one forms are used as the basis. One forms are something that have an integrand in it. It's not subject to this video, but just generally wherever you see a dxi, then you have a one form. A two form would be dxi wedge with dyi, something like that, and so on. Alright, we can generate new coordinate curves or axes from some chosen set of coordinates xi in the form, well, here we have our Cartesian coordinates x, y, z, and for the sake of this video we'll use three-dimensional Cartesian coordinates, but in general this applies in any dimension, but just for the sake of the video, because it's familiar to people watching, we'll use Cartesian coordinates in 3 dimensions. So we've got x, y, z, and we want to transform them to the generalized coordinates x1, x2, x3, and of course the map that takes us from Cartesian coordinates to these generalized coordinates is one-to-one and invertible, and we rely on that. And that was also in a previous video elsewhere. So the position vector becomes r as x times e subscript x, this object here, and then we can express the x, y, and z in terms of these generalized coordinates x1, x2, x3, as we've done here. There we go. Now each coordinate curve or axis is obtained by varying one of the coordinates while holding all of the other coordinates constant. So in our three-dimensional case, we hold x2 and x3 constant, and we'll just vary x1. And it'll generate a whole lot of curves. Just like we take the position vector here, and we hold y and z constant, and then we vary x, we'll get all the coordinate curves that make up all the x-axis throughout Euclidean space. You can generate an infinite set of curves. Same here, if you hold C1 and C3 constant and vary x2, or hold C1 constant, C2 constant and vary x3. And what that looks like as a picture is this. Here's our first one here. Hold the second two, x2, x3 constant, and then just vary x1. And we'll generate this curve along here. And different choices of C2 and C3 will give us different x1 coordinate curves, and so on. Up here, if we hold C1 and C3 constant and vary x2, then we'll get a whole lot of curves like this. By changing C1 and C2, we'll position these curves elsewhere throughout the space. And eventually we'll cover the entire space with an infinite set of curves, and so on for the third axis here. In n dimensions, we'll have n number of these axes, of course. Alright, and the basis vectors are formed by calculating the derivative of the position vector along each of the coordinate curves. So along the first one here, dr dx1 will give us this vector here. dr dx2 gives us this one, dr dx3 here. They are orthogonal to each other, but not necessarily of unit magnitude. They are tangential to the coordinate curves, and at each point all three of these vectors are orthogonal, as I just mentioned. Alright, now coming back to the fact that x, y, and z are functions of the generalized coordinates x1 to x3, and in turn, because they're invertible and one-to-one, then we have x1 as a function of the Cartesian coordinates x, y, z. That's what we have here. Now we can define coordinate surfaces by x1 as a function of x, y, z equal to c1, some constant. x2 as a function of x, y, z is equal to a constant c2, and x3 is as a function of x, y, z is equal to some constant c3. And then obtaining the following derivatives will give it the basis 1 forms we need for the space we're interested in. So del nabla x1 or dx1, dx2, dx3. Now what's key here, and we'll have a look at a picture of these in just a moment, but what's key here is a set of basis vectors and basis 1 forms are referred to as forming a coordinate basis or holonomic basis because they are derivatives of the coordinates. They are derivatives of the coordinates, but not necessarily of unit length. So both basis vectors and 1 forms may not be of unit length, so that's another point to just to make clear, just reiterating that again. So here's a coordinate surface in blue, and it's achieved by setting x1 coordinate as a function of xyz equal to a constant. So x1 is just a constant. If you think in three-dimensional Euclidean space, if you choose a number along the x-axis, say x equals 5, then you'll see there's a plane formed, and that plane is perpendicular to the coordinate axis, to the x-axis, and it covers all. It gives you a big surface in the y-z plane. So by choosing x equal to some number, let's say plus 5, you'll get a coordinate surface formed by the plane that involves the y and z axes. And that's what this picture is trying to show here. And in curved space, it'll obviously be curved. And you can see here that del or dx1 is perpendicular to that surface, to that coordinate surface. And that's the idea. So you get a set of these are forms of basis. Now, I haven't been able to put the other 2 coordinate surfaces in because the diagram would get too messy. But if I did, you'd have 3 of these perpendicular vectors here. 1 forms. dx1. Shouldn't call them vectors because they're not. They're 1 forms. dx1, and we'll have 3 of those. And again, they'll be perpendicular to each other, but not necessarily of unit length. Only 1 coordinate surface and one form is shown here for the sake of clarity of the diagram. Alright, next one. Now, as an example, xyz, Cartesian coordinates, and we're going to let our generalized coordinates be spherical polar coordinates now. So x1 is r, x2 is theta, x3 is phi, and the transformation is x is this, z equals r cos theta, and so on. Now, the position vector is familiar form. Write that out. Alright, now the partial derivatives of which give the basis vectors in this new space. Here we are. E subscript r is this object here, which is dr, the position vector, the partial derivative of the position vector with respect to the coordinate r. That gives us this object. E subscript theta, d theta, dr d theta gives us this object here. E phi, d phi gives us, and the partial derivative of the position vector with respect to phi gives us this object here. Now the metric for this space is given by GAB as E subscript A dot E subscript B, which if we do that for each of the coordinates r, theta and phi, we'll get this object here, 3 by 3 matrix, of which only the diagonals are non-zero. All the other terms are 0 because they're orthogonal to each other. And what we find now, and here are the metric terms here. Right. Next one now. Not all these basis vectors are of unit length. If you carry out the calculations, E subscript r dotted with itself will give you 1, E subscript theta dotted with itself will give you r squared, as we saw on the previous page. E subscript phi dotted with itself will give you r squared sine squared theta. Now, if you take the magnitudes and the norms of each of these vectors, you'll get 1 for the first one. For this one, you'll get r, the norm of E subscript theta. Magnitude of E subscript theta will give you r. Magnitude of E subscript phi will give you r sine theta. Now, however, these basis vectors now are orthogonal to each other, but as you can see, they're not of unit length. Okay, now that brings us to the next part. A non-coordinate basis. What is meant by a non-coordinate basis or a non-holonomic basis is one in which the basis vectors or 1 forms are orthonormal. And to be orthonormal, that means they must be orthogonal to each other and of unit magnitude. So these take the form E subscript I is dr dxi times 1 over the modulus of dr dxi. And for the 1 forms, E superscript I, contravariant I, is del or dxi over the modulus dxi. Where they obey the condition ei dot ej, they follow the Konica delta, delta ij. So they're orthogonal to each other, but they're also of unit length. In the case of our spherical polar coordinates, we can come up with an orthonormal basis, E R hat, and we put the hat over the correct symbol to indicate that it is a unit vector. Okay, E hat represents a unit vector, and in this case here it's equal to E, the normal E subscript R, but E theta hat is 1 on R E theta, E phi hat is 1 on R sine theta times E phi. And these dotted with itself, E phi hat dotted with E phi hat, will give us 1 when that operation is carried out. And that is that for coordinate and non-coordinates, or holonomic and non-holonomic bases. The first there, derivatives of the coordinates, but a non-coordinate or non-holonomic basis is then a basis involving objects of unit magnitude.